How do you tailor a polymer so that it can be 3D printed? The answer to that question lies in the broader context of how do you tailor any polymer for processing by any method for any given end function. So, for instance, take the natural state of a very high molecular weight polymer material which exists as this random coil. From this highly disordered state, if you remove thermal energy, you will be able to convert it into a more ordered. The thermodynamic barrier in terms of the loss of disorder to generate order is extremely high for high molecular weight materials, because the degrees of freedom that the material experiences is so high in this amorphous or random coil state. The thermodynamic barrier, the entropic barrier, is very high. In addition, changing this from the polymer from the disordered state into an ordered state is the equivalent of taking a bowl of cooked spaghetti and putting it back in the box. Depending upon the molecular weight of the polymer, its chain configuration, its chemical structure, and so on, the extent to which you can create ordered domains, the fraction of them, the size of these, the orientation of them, all dictate polymer properties. How does this translate into properties? Here is an idealized plot of the resistance to deformation, so a measure of mechanical properties as a function of temperature. For a fully amorphous material, as is the case for a lot of polymers, the solid declines in strength as the temperature increases to some extent. It goes through a transition which is referred to as a glass transition, TG. Then it continues to go through a decline, but you have an amorphous or a rubbery phase, and then you go through the final fluid stage to make different shapes. A fully crystalline polymer, on the other hand, would at a much higher temperature go through a sharp melting transition that is shown over here, after which it turns into a melt. Polymers that are semi-crystalline will have two transitions. One, they will go through this glassy region and then go through a rubbery phase and then melt completely at a higher temperature. The variations of these TGs and TMs according to the structure allow a way in which you can change the processability as well as the mechanical properties and hence the design capabilities of the product. In addition to molecular weight and crystallinity, you also have chain configuration that can be controlled by polymer chemistry. You have an example of a linear thermoplastic. These chains are completely straight, squiggly lines or straight lines, but on the other hand, in B, you have a branch structure where you have monomers that have been synthesized off the chain as well, the main chain. So these represent different ways and different resistance to crystallinity as well. If you react the material further, you could constrain the mobility of chains, multiple linkages to other chains, and this is called cross-linking. And so you get a thermoset material. And if you have a lot of those cross-links generated through reactions, you have a net thermoset. These last two categories will be looked at in Module 2 when we look at reactive polymers. In Module 1, we'll look at these combinations. We have looked at the fact, especially in step polymerization, that you could have more than one monomers in the main chain. Even in chain polymerization method, addition polymerization, such as in the case of the ABS material, acrylonitrile butadiene styrene, you have come across copolymer term where there's more than one monomer. You could have the distribution of those monomers in the polymer chain in a random way, in a perfectly alternating ordered manner, in blocks or as graphs stuck to the main chain. Polymer chemistry affords you all these different possibilities, and along with that you can tailor a lot of processability as well as properties. So molecular weight, crystallinity, chain configuration. In addition, you can add different ingredients into the polymer. For instance, you can add colors and create a whole lot of range of products with different appearance that can be customized. The second aspect is you can change from a purely insulating material to a highly conducting material and create electrical circuits by 3D printing. In traditional processing, the ability of extending the functionality of a polymer to be able to address some of its limitations in its unfilled state have been addressed by additives as well as different fillers. You can change the conductivity, you can change the tackiness or adhesiveness. You can improve the mechanical properties. You can help its processability, its stability, appearance. Aerospace industry took advantage of this in a great manner by creating composites with strength to weight ratios that were comparable to metals, be able to take the weight of the components in a big way. Automotive industry has followed suit. You could tailor properties depending upon the proportion of the fillers, the types of fillers, their geometry and distribution, the bonding between the two phases or multiple phases, as well as the extent of orientation. In the automotive industry, tires have for long served the purpose of composites when particles of carbon black were introduced into the tires to improve their strength. So granules were hard and brittle, the matrix was ductile and soft, and you created a product that had isotropic properties that could be long lasting and have a lot of impact. Fiber reinforced composites, the fibers can be individual fibers that are oriented, or they could be woven fibers as well. They could be not oriented at all, and you could get isotropic properties as well. Fiberglass is a very common example. In the natural state, bamboo and wood are examples of fiber reinforced composites. Of late, there are a lot of natural fibers that are available to be able to create sustainable products. In addition to fibrous or particulate composites, you could have laminar composites as well, which is of great interest because 3D printing in many forms is a layer by layer process, and so you could extend this synthesis of laminar composites very well into the architecture. There are a number of coatings, as well as more commonly you'll see cardboard and plywood as familiar examples. Different foam products are also useful for structural applications. Over the last couple of decades, the introduction of nanoscale fillers, they have very high surface area and associated surface energy that allows them to be able to modify the polymer properties in a very dramatic manner at very low concentrations of materials. They can be clay or cellulose, which are natural products, and additives coupled with 3D printing offer an extension of the design window for engineers to create new products using 3D printing. So to summarize, the chemistry and molecular weight can change to change the attributes of polymers. Those changes can then affect not only properties but also processing conditions, the ability to create shapes, the method to create shapes. We will see during lecture 3 that there are several processes available by additive manufacturing to convert thermoplastics into useful shapes. The introduction of fillers and additives allow us to build complex systems with expanded attributes, design features, and functionality, and that can be taken advantage of in additive manufacturing as well. In the next class, we will build from this introduction and look at specific properties of thermoplastics that define how they can be processed, how they can be used. Here you see a fully 3D printed car by Local Motors.